I think in the beginning, a difficult concept to grasp, especially if you come from a tradition of time series analysis where you keep thinking of the shift in time. But if you think of it as an averaging of the neighbors, and that's really one way to bring space into the model, then you're on the right track. What we're going to do now is move on and look at how we get to a structure for the spatial covariance. Essentially, we're looking at a map, if you wish, or data on a map as a joint distribution. And that joint distribution is characterized by moments. These moments are characteristics of the distribution, like central tendency, a mean, variability around the central tendency, that's your variance, and then cross variability between, in this case, locations, because it's the same variable distributed at different locations. So how is the cross variability of that variable between different locations? And that is the spatial covariance. So the tricky part is, how do we estimate this spatial covariance? And this is the same problem as we discussed yesterday. Covariances are in n square, whereas the observations are in n. So again, here we will have to impose some structure to make this a manageable problem. So formally, the spatial covariance is, as I said, it's an autocovariance. So auto means it's the same variable. So there's the same y, but at different locations. So we have y at I and y at j. So if we're looking at crime, it's crime at one county and crime at another county. And this is just straightforward what a covariance is by definition. Spatial covariance is when this covariance between locations I and j is non-zero. Now that's really not spatial. That's just non-zero covariance. Where it becomes spatial covariance is where the pattern of non-zeros has some spatial structure to it. So there's a difference between just having a non-zero covariance, that's just a characteristic of the data, a characteristic of the variable that you're describing, and what we would call, when we start to call it a spatial covariance, which is where the structure of the non-zeros has some connection to spatial structure. And how do we get to that? We get to that in three different ways. And we'll focus particularly on the first two. In the Frontiers course, we'll also spend some time on the last one, which is a non-parametric approach, letting the data define the structure, the spatial structure, which is a lot more difficult to do. But we'll focus on two particular approaches. One is called direct representation, where in essence you impose a functional form on how the covariance changes. So the covariance is how this variable that we're looking at co-varies with the same variable at another location, how that changes with the distance that separates them. So basically we are a priori imposing a functional relationship between the strength of the covariance and the separation distance between the two locations. That's why it's called direct representation. And this functional relationship will have some parameters which we'll then try to estimate from the data. The second approach, and more common in applied work, is that we get to the covariance by starting with a spatial process model, which is essentially a relation, a regression, that specifies how the observation at a location is linearly related to observations at other locations. So from this specification, we then end up with a particular structure for the spatial covariance. It's very important to keep these two separate. And you get from one to the other. So we instead of specifying a function for the distance decay, if you wish, of the covariance, we specify a function for the variable itself. And then out of that comes the structure of the covariance. And well, I'll elaborate this in a few minutes with some specific examples where you see how by starting with just a very simple autoregressive relationship, you end up with very complex structure for the spatial covariance. And so depending on the situation, it will be more effective to impose a distance decay function, which is the direct representation, or to start with a spatial process model and then end up with the covariance that follows from the spatial process model. And it also depends on the interest. Sometimes the interest is in the covariance as such. Sometimes, for example, if you want to interpolate, Kriging, which is an interpolation technique, exploits the covariance structure directly. But in our case, we'll tend to be more interested in the regression models, in the spatial process models. So we have to know what the covariance structure is, because we'll exploit that in our estimation methods, but that's not a primary interest. The primary interest is in the parameters of the regression specification that we start with. So it's important to distinguish these two. Let's just start with direct representation, which is the easiest. So as I mentioned, we specify a functional relationship f, which is a function of some parameters theta and the distance I between I and j. And we need a distance metric, we need a functional specification, and then we get the parameter. Now this all sounds very straightforward. There are some catches. Because what we're really trying to do is fill out all the elements of this covariance matrix. And there's some constraints. For example, as you all know, you cannot have a negative variance. Such a concept does not exist. In multivariate extension of this is that you cannot have a negative definite covariance matrix. The matrix has a characteristic which is similar to being positive and negative for a scalar, but it summarizes the whole structure of the matrix. It's much more complex. I don't want to spend too much time on this. If this is, if you're not comfortable with this, then my spending 5 minutes on it is not going to help you. You just have to take my word for it. It's a characteristic of the whole matrix, and basically you don't want this to be negative. Let's just put it that way. So that means that you can't just stick in any function, and you can't just use any parameter value, because for some of these parameter values, you'll end up with covariance matrices that are not positive definite. It's like specifying a function that gives you a variance that is negative. You can't do that. And so there are constraints on the types of functional forms you can use, on the parameter space, the values that the parameters can take, and on the distance metrics. And this is something that sometimes is forgotten. So the covariance, the spatial covariance matrix that you end up with has to be, as I put it here, a proper covariance matrix, meaning a couple of things. There has to be distance decay. Remember Tobler's law, as things are closer, they are more related, which also means as they are further apart, they're less related. So there has to be some structure in the covariance that is compatible with a distance decay. And so you can't have the covariance increasing as locations are further apart. That is counter to this distance decay argument. And in fact, as we'll see a little bit when we talk about estimation, we need this distance decay, or otherwise our estimation methods don't work. They all require, and let me just digress for a minute, they all require asymptotics. Asymptotics means you go to the limit. And the rationale is that if you have distance decay, then as we grow to the limit, we'll have more and more pairs of observations that are so far apart that they're in fact not correlated. And so that gives us the information then to carry out our estimation. But if that's not true, if everything depends on everything else equally strongly, then we don't gain by going to the limit. We don't gain information because everything is equally correlated. Nothing new gets added. So we need this distance decay. We need it. And in fact, this is not unique to spatial analysis. It's the same in time series. You need some decay to get at these asymptotic properties. Secondly, I mean, this is kind of obvious, but the covariance has to be symmetric. Covariance matrices are symmetric. So you can't have asymmetric distances, for example. We will see later, you can do that in the process approach, because the process then gives you the covariance matrix, and that's always a proper covariance matrix with the right parameter space. But here, we're actually specifying directly, and that's why we call it direct representation. We're specifying directly what the values are for every ij, every element in the covariance matrix. So we have to be very careful that we don't do things that are not allowed. And one thing that's not allowed is that the covariance is asymmetric. It has to be symmetric. Then the tricky one, because symmetry is obvious, you can see it. And distance decay is also obvious, you can see it. But this positive definiteness is not something you can just see. You have to compute things to verify that the matrix is in fact positive definite. Just having a matrix with positive numbers does not guarantee that it's positive definite. That is a little bit counterintuitive, but it's more complicated than that. So just having positive covariances is not enough. You really have to check that the structure of that matrix is such that it is positive definite. And let me give you an example. Let's think about points on a line, and it's very simple. They're 1 unit distance apart each, and we computed distances, which gives us a distance matrix D, and I hope it printed out okay. I think in the past we've had some problems with these yellow and later red printing out properly, but this is a distance matrix, and distance is symmetric. So with this in hand, how do we get our spatial covariance matrix? We will take these distances and plug them into a function. And that will give us a number, which then, because we say so, is the spatial covariance between any pair of observations. So we have the 5 points on the line, and the distances are just 1, 2, 3, 4, and it's a nice band matrix. This is typical of a distance matrix. So now let's take a function, say a negative exponential, and we will plug these distances in that function, and out of that comes a number. So we take the negative exponential, the covariance between any I, y at I, and j is the exponential of, say, minus 0.2. Minus 0.2 is our parameter. We set it. Typically, you will try to estimate this from the data, but in this example, and then we plug in the dij. So for any pair, let's say between location 0 and location 1, the distance between these two is 1 unit, just to keep it simple. So therefore, the covariance between these two is e to the minus 0.2 times 1 for the distance, so that's 0.82. And you do this for all of them, and you get this nice covariance matrix, which has, if you can see it, the values decay 0.82, 0.65, 67, 0.55, 0.45. So there's a nice band of decaying parameters, and that is your covariance matrix. And then you have to check, and one quick check is to compute the determinant of this matrix and make sure it's positive, and then you're fine. The tricky part is that in practice, there's two things that you have to specify before you can estimate the parameter. You have to specify the function and also the distance metric that you use. And scale matters. For example, a common function that is used is 1 over distance. Okay. Now, 1 over distance will give you a very different number whether you measure the distance in meters or in kilometers. There's a big scale effect. And one thing that happens inadvertently when you mechanically use these things in software is you're not thinking about the units. And you're computing 1 over something really big. And in essence, it's all 0. Okay. And these are the kind of gotchas that happen, and it's happened to me. You're not thinking about the units that your x and y coordinates are expressed in, which is going to drive the units that you get for the distances between your points. And you know, these distances are in meters, and you're looking at distances between cities in meters. Those are big, big numbers. So 1 over that is basically 0. And if you're not careful, you end up with a nonsensical covariance matrix. So there's a lot of things you have to do. You have to be careful with these distances. There's also problems with a lot of functional forms. That's why the negative exponential is so popular. If you divide by 0, you have another problem. So if two locations are in the same location, now you might say, well, when does that ever happen? Well, it happens more often than you think. It can happen because of rounding errors, but also, say, in real estate analysis, if you have high rises and you have apartments at different floors, they're all in the same X and Y location. So you need to think about how you deal with this. And if you do straightforward 1 over distance, it's not going to work. Another case where this pops up, and this may not be immediately obvious, is when you use socioeconomic distances. When the difference between the socioeconomic makeup of two observations is not enough, you end up with a 0 distance. And there's an example of this. If you look at the African American population as a characteristic of a state, there are 2 states, I think it's Vermont and Wyoming, that are basically identical. So the distance between those two is 0. And if you're not paying attention, and you know, you have your data and you crank and compute the distances and do 1 over distance, it blows up. So this is something that requires attention to the functional form that you use for the distance decay. And typically the most often used one is a negative exponential function, because it guards you from those problems. It's fine when the distance is 0 and it has a nice decay. As I mentioned, the metric matters, whether your distance is, what scale it is expressed in, especially if you do 1 over distance, but also in the negative exponential, you want to be careful not to have huge numbers going into these functions. And the problem, as I mentioned, and I guess I can go back, but it's not going to help us much because you can't see it very well, but this is a matrix with very nice positive numbers, but in fact its determinant is actually very close to 0. And so this is an ill-behaved matrix. It's not a real major problem because it's just an example, but this is the kind of thing that sneaks up on you if you're not careful. And in practice, the determination of the parameter space, so the values of the coefficient in your negative exponential that give you proper covariance matrices, is something you have to really watch out for. That's something that is, you cannot just let that be anything, because there is a range in which you will get a non-positive definite covariance matrix. And this is really subtle, because you look at these numbers and they look just fine. But the structure of the matrix is not proper, which means that the distribution you're trying to characterize actually doesn't exist. And so that's really the consequence of this. You know, you're trying to characterize a joint distribution. This is how we started. How do we characterize this? You know, we take the mean, we take the variance, then we take the covariance. Now, if the covariance is incompatible with something that exists, then you're in trouble. Did you still have a question?
Yes. Could you do some sort of sensitivity analysis in the sense of changing your parameter from O2 to minus O2 to something else, and generate it, then recompute the determinant, and as long as it gets more positive?
Well, the problem is the sensitivity analysis of the the matrix. Basically, as long as it's positive, it's fine. Okay, so the closer it gets to 0, the more ill-behaved it will be. It's similar to multicollinearity. You're familiar with multicollinearity when two explanatory variables are highly correlated. If they're identical, then the correlation is 1 and your matrix, your cross product matrix is singular, so it blows up. But if they're close to 1 correlation, the matrix will be near singular, but it won't blow up. And it's a similar thing. It's about characterizing the joint distribution. So we have to keep in mind that the characteristics of this distribution have to be proper characteristics. Now what it really relates to is whether the data are rich enough to provide you information to characterize that distribution. It's the same thing if you're done any econometrics and error components models or variance components models. These are models where you take the residuals of a regression and try to get an estimate of pieces of the variance, say a sigma 1 squared and a sigma 2 squared. But there's nothing that guarantees that the data actually are collaborating with you on that. So you can stick this in software and out comes an estimate that says sigma 1 squared is -2. Well, it can't be. Now, what does this mean? It means you're trying to force a model on the data that the data doesn't support. Similarly, if we specify some fancy function for the spatial covariance, and we try to force this on the data, and the data says, no, this is not how we are distributed, it will come up with these nonsensical covariance matrices. So that's the way I like to think about it. So let's take, before we start with the spatial process models, let's take a quick 5-minute break, and then we'll revisit this, because this is a whole new section. I'd like to cut it here and then have more of a consistency later on. What are we doing with our thing? Julian knows where we can get it. Do you have one? Yeah, well, these guys have one. They're just changing. Doesn't matter. They'll give us about they don't know. Yeah. Same So you see the Nutella? You eat the jar? Yeah, you can't eat too much of it. The kids like it. I like it too. That's why I got mine a lot. Yeah, full. Okay. Too much sweet? Sweet. Well. Yeah, but in the housing data, it's an issue, because the housing data, you could think, if you have all the sales, then you have the population. If you have a sample of sales, she has everything.
Yeah, but that's because she has the tax.
Yeah, right.
Yeah, that's what I said. Okay, it's like this in idea, right?
Yeah.
You would have to build a model for the data that you have.
Exactly. And that, or you can think of it as a sample, where the sample of the sales are a sample of all the houses, so then you use the sales data to interpolate values for the other houses.
And then, for example, when you have a survey like India, then it has to be represented at the spatial
At the
scale.
spatial scale, yes. Right. It's getting there. And one thing that I don't want to forget, I will need your keynote presentation next week for semiconductor, because I need to put it in. The way I do this is, no, I need the actual keynote. Yeah, because I need to integrate it. See, this is one long presentation. Otherwise, this thing gets goofed up. Since I selected it, I thought we were going to do it yesterday. Oh, okay, one more. It's cell that, let's start over. Oh, you did that? Oh, that's right. Did you replay it just to make sure that it works? Oh, yeah, it's being recorded. I thought you did yesterday, right? Let's replay it. I have nightmares about this stuff. No, we did it at home and it worked fine. But I have nightmares about this stuff. Let's just get rid of it.
It's like church.
I know. With the person in your face, like giving the sermon, you know.
Go to hell.
¿Eres colombiano? Ah, de México. Hay dos, tres colombianos. Hay que saludar. ¿Qué tal? Por acá 2 años, dice que ya a punto de terminar. Y luego te quedas acá. Claro, siempre seguirá por ahí alguna relación, ¿no?
If I put zeros, commit all those X's zeros. I know that yeah, and I know it's coming.
En Missouri,
Make a note.
bajito, es al sur. Bueno, voy a hacer 3 papers. Bueno, estoy trabajando en 3 papers. 2 de ellos son sobre crecimiento y desarrollo en zonas rurales en México. Y el otro, que es por lo que estoy acá, en Missouri tenemos algo que son los sales tax holidays. Es que un fin de semana no cobran los impuestos sobre ventas. Entonces, pero las ciudades, cada ciudad y cada county tiene la opción de participar no participan. Entonces acá es donde estoy viendo estas interacciones, como si yo soy una ciudad y tú eres otra, y somos vecinos, bueno, pues mi decisión te va a afectar a ti y la tuya va a afectar a mí. Entonces yo tengo que empezar a imaginar cómo tú vas a reaccionar para entonces yo moverme. Entonces yo hice unas estimaciones, pero ahora que veo todo esto digo, mis estimaciones están completamente mal. Y obviamente me salió no significativo, por ejemplo, el indicador que yo estaba usando para medir eso. Tengo una mala especificación porque, por ejemplo, yo no estaba manejando, o sea, lo que estaba usando era nada más contar el número de ciudades que hay alrededor. Y yo estaba argumentando así como que entre más competencia tengas, a lo mejor es más incentivo a participar, ¿no? A atraer más clientes, ¿no? Pero parece que eso no es suficiente porque no me está cambiando nada, no está saliendo significativo. Entonces digo, bueno, quizás si doy una mejor especificación, como por ejemplo la matriz esta de los weights, ¿no? De las distancias o con población, exactamente, ponderando por
It's a quick time, so it has everything from yesterday on.
no son vecinas, ¿no? O no son competencias. Pues sí, por eso que estoy acá. Pero tengo que ver porque mi variable dependiente es dicotómica, normalmente es participo.
This is the data in terms for the report. Our company will have all this
On the housing value example, for their apartments or any phenomenon, but when they're all stacked together like that, you just eliminate duplicate points. How would you work around that?
You can do either one. I mean, really depends what you're working on, but you can just sample randomly one from all of them. Or you can create a neighbor structure where you say, I mean, not only across space, but also vertically. So then they all become neighbors of each other vertically. If they are neighbors, yeah, that's.
these guys?
Well, yeah, go ahead.
We were wondering where this discussion of the covariance and the Y's is leading.
Oh, look at this
I
too.
mean, why is this characterizing the dependence in the lag model? Is that what this topic is leading to?
It's leading to the structure of the spatial covariance matrix that you get, and the fact that the covariance matrix is not the weights matrix. So when you put a weights matrix in a lag model or in an error model, the covariance that you get is not the W, but it's more complex than that. And depending on the kind of model that you use, you will get different types of covariance structures. And specifically, as we'll see later today, the main difference is between the covariance basically tells you how strongly related are pairs of locations. And what we're interested in is what is the strength of this covariance? How does it decay with space? Is it global or is it local? And for some models, the structure of the model gives you a local covariance. Okay. And for other models, the structure of the model gives you a global covariance. So each of these models, let me say autoregressive or moving average or conditional or simultaneous, they each yield a particular type of covariance structure that has a spatial structure. And what is important is that you know what that is, so that when you implement, when you choose a specification for your spatial model, and you say your theory says it is a local spillover, local externalities. Only the immediate neighbors are affected, nothing beyond that. Then you cannot use an autoregressive model because that implies a global correlation structure. And vice versa. If you specify a moving average model, that yields a local covariance structure, so then if you need a global covariance structure, that's not the proper model. And this is also important in a more advanced context when we look at some of the newer techniques, some of the semi-parametric techniques, some of the autocorrelation consistent spatial covariance techniques, and that these pertain to very particular covariance structures and that typically do not allow global covariance. So I think it's important to know what you're getting into when you start using these models, and that some of these may not give you what you want. And that's why we're going through this exercise of seeing the different types of ways in which we end up with a spatial covariance matrix, because that's really what we're trying to model. We're trying to model the pattern of the data. The pattern of the data is the joint distribution of all the data by their location. So how do you characterize that? You characterize that by the moments of the distribution, the mean, the variance, the covariance. And then, if you want to go on top of that, you assume a particular mathematical functional form, like a normal distribution or something else. And that's how we characterize this. And it's the only way to do it because there isn't sufficient information. We're trying to characterize something that is about interaction, and we only have one dimension of observations. That's the bottom line. Okay. So far, we've looked at how we get the covariance function directly. So we say, we need a spatial covariance function. We're going to make it a function of the distance that the pairs are apart. And this is very along the lines of how geostatisticians think about the problem, because they think about the problem as a prediction problem, as an interpolation problem, where you use the covariance matrix to get better precision for your interpolation. The second approach, the one that we'll focus on now, does not directly impose a structure for the covariance matrix, but you end up with a structure from the specification of the spatial process model. And it's an indirect process. And let me just start by refreshing your memory and give you an example from time series, which is a classic textbook example. If you have a first order autoregressive process, so this is a process that relates y at time t to y at time t minus 1, and then some error term. So what we're interested in is the covariance of all the y's at all the points in time. Now that covariance, you get that from basically solving this regression specification and finding out what the resulting structure of the covariance is. This is a textbook example. You just solve this by substituting each time period, and then out comes, this may look familiar to you, this rho to the h, where h is the number of time periods you are separated, divided by 1 over rho, 1 minus rho squared. So this is the covariance between any 2 points h periods apart. So we start with this simple regression, which is an auto regression, y regressed on y, and from that comes the covariance. So just to show you what it looks like, we plug in some numbers, because I'll show you the same thing on a line, which is a spatial model. So we plug in 0.2 for rho, and we get that the variance is 1.04 whatever, and the covariance is this expression. So what's the upshot of this is we have a full covariance matrix. First of all, the variance of y is not the same as the variance of the error term. The error term variance is 1. the variance of y after we have this autoregressive process is actually larger than 1. And then we have this nice band system where as we move further and further away, we have smaller and smaller covariance. The other thing we see is that the covariance is the same no matter where you are, as long as you're 1 time period apart or 2 time periods apart, it's always the same. This is this notion of stationarity we talked about yesterday. The covariance does not depend on location. So the covariance between t and t minus 1 is the same whether t is 2000 or t is 1990 or t is 1980. It doesn't matter. What matters is that it's 1 period apart. And in space we'll have the same thing, or I should say similar thing. So correlation the same. So we have the bands. The variance of the process is not the same as the variance of the error term. The correlation and the covariance matrix follow from the process structure. So the process equation, the yt is rho yt minus 1, gives you the form for the covariance matrix. And now we'll see the same thing in space, but in space it's slightly more complicated. We're going to look at what we call a spatial autoregressive process. And a spatial autoregressive process relates the value of a variable y at location I to the values at other locations j through this spatially lagged dependent variable. So the spatially lagged dependent variable is the sum over j of wij and yj. That is the one we just saw earlier this morning with a parameter rho. And this is a very commonly used model for a spatial process. In matrix notation, and we'll see this back lots of time, we have the vector y, parameter rho, w times y is our spatially lag dependent variable, and then u is the error term. So what is the question? The question is, starting with this linear specification of the relationship between values of y at different locations, what type of covariance structure comes from this? Okay. And we'll see that with other types of spatial models, different covariance structures will follow from this. The most important thing I like to stress, because this is often a point of confusion, is that the covariance structure is not the same as the weights matrix. So let me put it differently. Even though your model specifies that there is a linear relationship between a location and its immediate neighbors, that doesn't mean that the spatial covariance is limited to the immediate neighbors. So if you're thinking in terms of how are things interrelated across space, you specify a model that only includes immediate neighbors. That does not mean that the interrelationship across space is limited to the immediate neighbors. In fact, it's the contrary. It's a global system. Everything is connected to everything else, following from the simple specification of a relationship between immediate neighbors. And that's an important distinction to keep in mind, because oftentimes when I see papers or referee papers, there's a confusion between the specification of the process, which is the W that goes in here, and the pattern, which is the covariance for the dependent variable that one is interested in. And that pattern is interpreted in terms of externalities or spillovers and so on. So if you specify a model that has immediate neighbors in it, and then you conclude that the spillovers are to the immediate neighbors, that's actually not correct. Because that first order model yields a covariance structure that implies spillovers to all the neighbors in the whole system, with a particular decay pattern that follows from the magnitude of your parameter. So the higher the parameter, the slower the decay. And so for all practical purposes, at some point, if they're far enough apart, and if the rho parameter is small enough, it will decay to 0. So for all practical purposes, there will no longer be any interaction. But conceptually, there's a difference between the neighbor specification in the process model and the spatial covariance that results from that for all the observations in the pattern. So in this particular case, we, and I mentioned this and I warned you that we are moving to matrix notation from here on. We get what is called the reduced form by moving first the spatially lagged variable over to the left side of the equation, and that gives us a matrix. This I minus rho W is again an n by n matrix. And then we solve, quote unquote, for y by inverting this. So we basically multiply each side by the inverse of the matrix, which cancels it out on the left-hand side and puts it in on the right-hand side. So then the covariance of y we can get from this expression here on the right-hand side, which is a matrix of numbers times a random variable, our error term. And using some standard manipulation, we get the covariance as the expected value of this cross product. This is a column vector, this is a row vector, so we get a full matrix out of this. It's basically a product of every possible pair, and that gets a structure like we see on the right-hand side there, a matrix, I minus rho W inverted, an inverse of a matrix, and then some random terms, and then another inverse of the matrix. Now, depending on what we assume for those random terms, we can derive what actually the covariance structure will be. But one thing is clear, it is not limited to the first neighbors, because these inverses, these are, even though W is full of zeros, 1 minus rho W is not, and it's full of non-zero elements. And so we're filling out the covariance because we have this inverse matrix. And I'll illustrate this with a numerical example in a minute. But it's very important to appreciate this difference, the difference between the neighbor structure that you build into the process model and the covariance structure that results for the pattern, if you wish. Because the pattern is really what we're interested in explaining. How does what happens at I depend on what happens on J? That is the covariance in the structure. And we get that covariance by saying, well, I is linearly related to its immediate neighbors. And after solving this out, we get this pattern of covariance that pulls everything together. So if we solve this, and we assume just the basic uncorrelated equal variance assumption for the error term u, then we get a spatial covariance matrix of the form sigma squared times I minus rho W prime I minus rho W, and the whole thing get inverted. And this is not a sparse matrix. Also, this is a problem in practice if we want to do this for large data sets, because we have to invert a very large n by n matrix. So if we have 300,000 observations, in order to get the covariance matrix, we have to invert a 300,000 by 300,000 matrix, which is not a trivial thing to do. And contrary to the weights, which are sparse, this is not sparse. So when it's sparse, you basically don't deal with the zeros. When it's not sparse, you have to deal with everything. So this is quite a challenge. Okay, let's see what this looks like. Again, we're starting on a line, and this will start to give you some appreciation of some of the complexities of spatial models as opposed to models in the time series. In time series, as we saw yesterday, it's one directional. It goes from the past to the future. In space, it's both ways. So if we specify an autoregressive model, we'll have to take the neighbors to the left and to the right. Now, why is this important? It's important because if you move over one, then the previous neighbor, you become the neighbor of your neighbor. which is not the case in a time series. In a time series, we just keep moving in one direction. It doesn't bounce back. In space, you are your neighbor's neighbors, so if I plus 1 and I minus 1 are the neighbors of I, then I and I plus 2 are the neighbors of I plus 1. And it comes back in there. And this simultaneity implies that you can't just solve this like we did for the time series textbook example, where you just simply substitute the previous time and you keep going until you get at time 0, and then you solve it out. You can't do this, because if you substitute the neighbor, you bring yourself back in. So if you would substitute in the expression for I, let's say as we have here in the bottom, y at I is a function of I minus 1 and I plus 1. And we substitute I minus 1 in there. I minus 1 is a function of I minus 2. We're fine with that. But I on the other side. So then we have y at I both on the left-hand side and on the right-hand side of this equation. And that is not what we want. That's not going to help us substituting this out and getting rid of it. So the difference between the time domain and the spatial domain is, in the spatial domain you have to deal with the simultaneity and solve the whole thing by having this reduced form we just saw, which requires the inverse of a matrix. There is no simple substitution trick as there is in time series. So as I just said, if you substitute, you see minus 1, I minus 1 depends on I minus 2 and I plus 1, same way, depends on I and I plus 2. So the simultaneity precludes simple substitution to solve this. You are your neighbor's neighbor. The simultaneity is the core of many of the complexities in spatial regression analysis. You can't simple substitute it out. You have to deal with the simultaneity in the estimation and so on in solving the model for the right-hand side. So let's just see what these numbers would look like in a spatial case. We have this process, very simple, on a line. The weights matrix is below. It's nice band matrix, band matrix, left and right, left and right, left and right, for all of them except at the ends. At the ends, they only have one neighbor. So the result that we had before is for rho, that the covariance was sigma squared times I minus rho W prime, I minus rho W inverted. And that gives us the full covariance matrix. So in this case, we have 5 observations. We'll get a 5 by 5 spatial covariance matrix. Right? And we plug in the value for sigma squared, which we take as 1 to keep it simple. We plug in the value of 0.2 for rho. So this you can't do by hand. You actually have to run it, the matrix inversion. I mean, you could do it by hand, I guess, but it's not very practical. And for any real size data set, it's not practical at all. So then we get this kind of matrix. And I just want you to take a minute and look at this and think back or refer back to what we saw in the time domain and appreciate the differences. So first of all, focus on the diagonal. The diagonal is the variance of the process. In the time series case, we saw that the variance in the diagonal was not 1. It's the same here, it's not 1. But it was the same at each point in time. Here it's not. So even though we start with a process where the variance, the variability in the process, so when we have a regression, we have y, rho wy plus u. U is the random part. Okay? U is the random part that drives everything. The variance of u is constant. But because of the spatial structure, the variance of y is no longer constant. That is a major qualitative difference between time series processes and spatial processes. And it has repercussions that go much further than what you might think. because a lot of the proofs, if we get really technical, the proofs of the properties of estimators and tests, they all assume stationarity, which translates into constant variance. Spatial models do not have constant variance. And so, right off the bat, none of these proofs apply directly to the spatial case. Everything has to be redone from scratch. That doesn't mean that the properties don't end up to be the same or very similar, but you have to establish case by case whether or not this holds. Some cases it does, some cases it doesn't. But the interesting thing is that even though we start with something that has a completely constant variance, we end up with something that does not. So the spatial process induces what we call heteroscedasticity. Now, where does it come from? It comes from the W. And remember, when I pointed out the structure of the W in this previous slide, I said, you know, there's a nice band of one left, one right, except for the endpoints. That's what does it. The moment the number of neighbors is not constant, you get this heteroscedasticity. That's where it comes from. The other thing you see is that the nice bands are gone. In the time series case, we had the same numbers following the diagonal as we moved out. They were all the same numbers in the same band. This is no longer the case. It's no longer the case because of the simultaneity. The spatial covariance structure comes from solving this reduced form, which is not a simple substitution. So you can think of it as bouncing back and forth through this simultaneous process. And because the weights matrix has unequal number of neighbors, this creates differences between first order neighbors and second order neighbors and so on. So the structure of the matrix is much more complex. Although, if you look at it carefully, you do see a decay. You do see that locations that are further apart from each other tend to have a lower covariance. So the decay is there. The structure is much more complex than in the time case. And most importantly, the induced heteroscedasticity, the induced non-constant variance, is something we have to deal with. Similarly, if we standardize it by the variance, in this case now the variance will be different for each location, we get the so-called spatial correlations, which similarly show the decay effect and also show a lack of constancy along the bands. So in contrast to the time series case, the variance is not the same. So to compute the spatial correlation, we actually have to take these different variances into account. So correlation is a covariance divided by two variances. I mean, the square root of two variances. If the two variances are the same, it's always going to be the same divider, but here they're not. So here you actually have to pay attention, what is the variance of I and what is the variance of J, because it's not the same. So you have to compute this like a regular correlation, not like an autocorrelation. And we see this is very typical. The other thing to remember about this, there's no zeros here. So everything depends on everything else.
What exactly do you mean by the bands? The top and bottom row?
If you know, the bands are, if you follow the diagonal of the matrix. So if you have the ones on the diagonal, right? Then the row right, this band right above it and this band right below it are the observations that are 1 unit distance apart. In the time series domain, those values are all the same. So in the time series, the correlations between 2 points that are 1 unit apart will be the same everywhere. Here they're not. Okay. So this is another form of non-stationarity. That's what I mean by the bands. So the structure of the variance-covariance matrix for a spatial process is a lot more complex than its counterpart in time series. And this reinforces again what I've been saying several times already, that spatial processes are not simply time series processes in 2 dimensions. There is an additional complexity that comes to it. So to summarize this, the spatial process versus the time process.
In regression with simultaneity, I'm used to seeing instrumental variables or some other way of dealing with simultaneity. You've done that with this matrix inverse thing, something with, I don't know.
No, we're not estimating here. We're simply, the question is, when you have simultaneity, you use instrumental variables. We will, when we get to the estimation, use instrumental variables. But this is simply showing you, we're not estimating anything. We know the value of the parameters. So with the value of the parameters in hand, given this autoregressive specification, what is the structure of the covariance? And the main point to take home is that the variance is not constant, that we don't have this band thing anymore, that the complexity of the structure of the covariance matrix is much greater than it is in the time series case. And the cause for this, the reason for this, is the simultaneity. It's not simply a one-directional progression as it is in time, but there is feedback between the neighbors at each point. And the moment that the weights matrix is no longer identical for each location, then this feedback will create asymmetries, if you wish, in terms of how much feedback there is from one neighbor on the other. And that's why I kept, what I could have done is connected the endpoints on the line and say, okay, the beginning point of the line is really connected to the last one. And so pull them together in a circle. Then we don't have this problem, because then each location will have exactly 2 neighbors, and then we have a much simpler situation. In practice, that it doesn't work that way. In practice, in fact, it's much more complex than this. In irregular layouts, you have a whole distribution, as you saw in the lab demonstration yesterday afternoon. When we look at the distribution of the number of neighbors for a particular weights matrix, it can be highly irregular. And as a consequence, the structure of the spatial covariance will be highly irregular as well. Okay. So now it's, maybe I shouldn't do this, but I want to do this because I want to make sure that you appreciate the difference between the conditional and the simultaneous models that we'll tackle later on. And this is just some very quick review. We make sure that everybody knows what a distribution function is. It's basically a mathematical description of uncertainty. Cumulative density function, the density function itself, these are the ways in which we characterize the randomness of a variable. Now, it's very important to keep in mind that this comes from us. We come up with these mathematical functions. Okay, that is nothing, this is something that we force upon reality. Reality, you know, we don't really know how it works. We know there's randomness, and we know that there is some, if you wish, some system to the randomness, and that there is some central tendency. Things, you know, when they vary around some common value. There's some spread around that we can use to characterize that. And if we're lucky, these two things in hand and a functional form like a normal distribution, then we know everything there is to know about the uncertainty in the system. Okay. But what if the functional form is not appropriate? Well, then we're in trouble, of course. And that's the tension between parametric and non-parametric. In parametric approaches, you assume a lot. You assume functions, all kinds of stuff. In non-parametric, you assume very little. And you rely on the data to give you that information. For example, we can take data say, classic example is height of people. You take the height of people and you compute the mean and you compute the standard deviation, and then you plot it like a nice bell-shaped curve. And you say that's the distribution. Or you can take the same people and make a histogram. And then say the histogram is really the description of the distribution. And this may not follow a nice bell-shaped curve, but it is the actual distribution. So non-parametrics takes the histogram approach. It lets the data get you the distribution, and whether this fits some mathematical form or not is really besides the point. In parametrics, and typically this comes from situations where you have less data, you assume a lot, and then you can say something about the phenomenon that you observe. So these things that we use to describe the phenomena are distribution functions. In space, it's all about the multivariate distribution. Even though I mentioned yesterday, the pattern is the observation, so we really only have one observation point. By making various assumptions, we will deal with these as if they are multiple observations. This is where the stationarity comes in. So in practice, we will deal with spatial observations as if they come from a multivariate distribution. So if we have 100 counties, the pattern that we observe in the 100 counties is really one observation of a 100-dimensional distribution. So we try to model the joint uncertainty in all 100 variables all together. That's the joint distribution. And then we can cut slices into this. We can say, well, I'm not really interested in all 100 together. I'm interested in one county. Now, this one county does not operate in isolation from the other counties. The joint distribution is the thing that drives how each county operates. Now, whether we look at all the counties together or at one county alone, it's still driven by the joint distribution. So if we look at the county alone, we call that the marginal distribution, which is, in essence, ignoring the 99 other counties. We ignore them, but they're still there because they drive the joint distribution. Another way to look at the one county is not ignoring the other 99 counties, but what we call conditioning on the other 99 counties. So we take what we see in the other 99, and that tells us something about the behavior of the one county that we look at. So in a nutshell, the joint density is always there, whether we use it or not. The joint density is what drives the pattern. We can look at individual locations, either ignoring the other locations, which is the marginal approach, or conditioning on the other locations. The approaches we follow in modeling come at it from two ends. One end is modeling the joint distribution. It's very ambitious, so it's a model for the pattern. The other approach is starting with a conditional distribution. Now, the problem is that if you start with the joint, you can always get the conditional distribution because of the mathematics involved, and I'll show you a very simple example in a minute. The other way around doesn't necessarily work, because if the conditions that you come up with don't work together to a proper joint distribution, then the system is broken. For example, if the system truly makes, you have 3 units, and the 3 units are all interconnected and interact, and that is the joint distribution for the 3 units. And you posit a model that says unit number 1 is only related to unit number 2, and unit number 2 is related to 1 and 3, and 3 is related to 2 and 1, the system is broken because it doesn't add up properly to the right joint distribution. So this is going to be the problem that we'll approach a little more formally later on, is how do we get, because it's all about specifying functions here. We're not estimating anything yet. How do we specify proper conditional functions that, when put together, give us a joint distribution that actually makes sense, that isn't broken. The other way is always easy because there's more in there. You know, the joint distribution is everything you ever needed to know about the pattern. So with the joint, you can get the marginal, you can get the conditional. The other way around is not that simple because you can't just specify anything you want. You have to make sure that, as in a sense, you put the pieces of the puzzle back together, that you end up with a joint distribution that actually makes sense. Those of you who've worked with non-normal data, for example, non-Gaussian data, if you have individual phenomena, say, that follow a Poisson distribution, that doesn't mean that the joint distribution of these is necessarily something compatible with the Poisson. That's a major problem you encounter in spatial modeling of discrete dependent variables or counts, for example. That's why the normal distribution is used so often, because with the normal distribution, you stay in the same family. If the conditionals are normal, the joint is normal. If the marginals are normal, the joint is normal. That's not the case for most other distributions. And so then things get very complicated. Just to give you a simple example, this is a simple textbook example. Let's take a normal distribution, multivariate, characterized by a vector of means and a variance-covariance matrix. And for the normal distribution, we know everything there is to know when we have these two moments. That is also not the rule. That's the exception. I don't know how many of you have worked with count data or other such data. It's a mess there. Things do not necessarily combine nicely. You have to really work this out case by case. With the normal distribution, there's no problem. You know the mean and the variance, you're done. With other distributions, for example, you need to know third moment, fourth moment, and so on before you can characterize it. You can always characterize any distribution by all its moments. But who wants to do that? In this case, one mean and covariance, and you're done. Okay. So let's give it some numbers. So the mean vector, 1, 2, 3, and this is a variance matrix. Now what we're interested in is finding out, given this is, if you wish, the driver of the joint variability of these three random variables. Okay. So this is what's behind the scenes and what's driving them. Now what we're interested in is, if we're just focusing on one of them, what is their variability? So for the marginal one, that's very simple. The marginal one is still, because it's a normal distribution, is normally distributed with the mean that we have in the vector and the variance that we have on the diagonal element of the variance-covariance map. So that's the easy part. So the marginal density, just as a refresher, essentially what we're doing is we're integrating out everything else. So we're basically seeing what is the variability of this one random variable, summing all the possible values that all the other random variables can take. That's in essence what we're doing. That's a marginal distribution. In the normal case, this is very simple. The conditional one is something else. The conditional variable, the conditional distribution, you're not actually summing out all the possible values that the other random variables can take, but you're taking into account what values that they do take. So you're conditioning on them, which is more information. See, when you take the marginal distribution, you basically don't know what values these other variables take. And so to play safe, you look at all the possible combinations that they could take. You know, in a discrete random variable, it's a simple summation. For a continuous random variable, it's an integration. So it's an infinite summation, if you wish. So you basically take all the possible combinations of values for all the other random variables, and then the remaining uncertainty is what your marginal distribution tells you. In the conditional case, we have some information. And we are conditioning on that information. So we're interested in the uncertainty of a random variable when we know that variable number 2 takes value 2, variable number 3 takes value 3. So that's more information. And given that information, what is left about the uncertainty about the first random variable? How is its mean affected, and how is its variability, its variance around the mean affected? That's really what we're interested in. And a very basic but operation that we'll use later on a lot is that the conditional density is simply the joint density divided by the marginal density of the condition. This is something those of you who've done Bayesian work will be very familiar with. This is the driver of all Bayesian analysis. So essentially, what is left of the uncertainty after you know something about this other random variable? You take the joint uncertainty, if you wish, the joint distribution, and you divide it by that. Now, this is very simply put. I don't want to throw all the integrals in here. This is just to get the concepts. So then you can play around with this and flip it around, and you get the joint distribution as the product of the conditional and the marginal. And this will be important later on. When there is independence, when there is no correlation whatsoever, then knowing this condition doesn't help you. That's the whole notion of independence. If the random variables are independent, then there is no covariation. The covariation is 0. So whether you know what the other random variables are or not doesn't matter, because they're not correlated. There's no information you can gain from observing them. If they're totally independent, it doesn't help you. But if they are dependent, then by observing this other one, you know a little bit about the one that you're interested in. That's the covariation that you exploit in the conditioning process. So conditioning doesn't help you if there is independence. Conditioning also only helps you if there is dependence, if there is covariation among the random variables. So if there is independence, then we have a simple, what we call a factorization here, where we get the joint distribution as the product of the marginals. Why do I do this today? Because we'll get back to this when we do maximum likelihood estimation. Maximum likelihood is basically the maximization of a joint density function. And a joint density function in the most classical cases is simply the product of the marginals, which is easy to do. In the spatial case, because there is covariation, that doesn't work anymore. Because you can't simply multiply these out as marginals, you have to do it this way. You have to factor out by using the conditionals, and as we'll see later on today, that doesn't necessarily work in space. So then we have to work literally with the whole thing, which means we have to work with the full covariance matrix, with the determinant of the covariance matrix, with the inverse of the covariance matrix, which is, by the way, an n by n matrix of the size of the data set. So that's one of the main complicated factors in estimating spatial models. But it all comes from here. It all comes from the simple notion of the connection between the joint distribution and the marginals. If there is no independence, then there is no longer the simple factorization of the joint distribution, which every textbook maximum likelihood method uses, because that's the simple way to do it. So in space, you don't get the log likelihood by summing up the likelihoods of the individual observations, because they're not independent. You get the joint likelihood by working out the likelihood for the multivariate distribution, that is, for all the observations in the spatial data set, which is a major difference. Now let's focus on the conditionals, and as I mentioned, given a joint density, you can always get the conditionals. That's simply a mathematical, very easy to do. But the reverse is not necessarily the case. To get the reverse, the conditions that we use have to be compatible with the joint distribution. And as a refresher, I don't know how much of a refresher this is versus totally new. If you, in a multivariate normal distribution, so if you had multivariate statistics, this is one of the classic examples, you can derive analytically what the expressions are for the conditional mean and the conditional variance. The conditional mean has another word for it. That's called a regression. It's the mean of a random variable conditioned on other random variables. In multivariate analysis, multivariate, you get the multivariation from the joint distribution, and then when you assume a Gaussian or normal distribution, the result up there is the classic regression function, where the conditional mean is the original mean, mu I, plus the regression part. And the regression part is a covariance part. This sigma I star is a row, you see here, is apart from the covariance matrix where you eliminate 1, and then you take the parts that refer to 2 and 3 in this particular case. Sigma star star is the submatrix starting at 2, so from the second row and the second column out, you have a 2 by 2 matrix. And this expression of the covariance times the inverse of the variance is in fact called a regression. And if your variables are a multivariate normal, this is how the conditioning works. Okay, if they're not multivariate normal, you can still approximate the conditional mean by a linear regression. That's where regression analysis comes from. But it's not exactly the conditional mean. Here, because of all the structure we've assumed, it is exactly the conditional mean. So we can work this out. And we find that the conditional mean is in fact this original mean that we had, plus a regression on the other random variables, where these are the regression coefficients. In other words, this has some structure to it that follows from the joint distribution. Now, if we say, I don't like this, I don't want this to be 0.616, I want it to be 0.3, then the system is broken. Because then these conditional means are no longer compatible with the joint structure that we had for the whole system to begin with. So we can always go from joint to conditional. This is what we just did. But to go back, we have to play by the rules. So to go back, we have to put our conditional models in such a way that they are compatible with the joint model that drives the whole process. And to illustrate this, if this is not a refresher, we can spend some time later to talk about this. But with the variance, it's even more so. It's this expression up there where you start with the original variance and then you subtract this matrix product of submatrices from the covariance matrix. You plug in the numbers, and here you see why conditioning is actually gaining information. Because if you work this all out and you just plug in the numbers, you end up with a conditional variance that is much smaller than the original variance of 2. Now, what does that mean? It means there is less variability around the central tendency, which means there is more precision. You have gained information because you've exploited the information that you observe in the other random variables. So if you think of these models as describing uncertainty in a random variable, there is a lot less uncertainty when you're able to condition on other variables than when you're not able to condition. And this is something you need to appreciate when you model these things. And it's very attractive to model something from a conditional point of view because you do better. But you can only do better if you know more. Because this conditioning assumes that you really know what y2 and y3 are. If you don't know that, is no good. And this is something that we'll see later on is maybe difficult to appreciate, the difference between conditional spatial models and simultaneous spatial models. In a conditional spatial model, you're conditioning on the neighbors, which implies that you know the value observed at the neighboring locations, which is a lot more information than in a simultaneous model where you model the whole pattern at once. So you model the neighbors, but the neighbors are unknown. The neighbors come out of the particular process that we assume. You cannot assume that you observe the neighbors when the neighbors affect you. You affect the neighbors. So if you observe the neighbors, then some of this interaction is already incorporated in the model. So it's not that one is better than the other, they're different. They're different in terms of the information that they exploit, the information that they use. When are they more appropriate? A conditional model is more appropriate if you're interested in prediction or interpolation. You get values at locations. You want to predict a missing observation, that is its neighbor. That's a conditional model. If you want to model the whole map, then you cannot use a conditional model. You can, let me rephrase this, then it's very difficult to use a conditional model because you have to make sure that these relationships, the different conditions, add up together, factor together to a joint distribution that actually exists. That makes sense. And we'll see in a few minutes, this is one of the major challenges in the formal probabilistic framework for spatial stochastic processes, is under which conditions do we get these conditionals to factor together to a proper joint distribution. And interestingly, this is the same, this mathematical framework is the same that underlies major simulation estimation methods like Markov chain Monte Carlo today, this day and age. A Markov chain Monte Carlo approach is used a lot in Bayesian analysis, is essentially trying to simulate a joint distribution by multiplying together conditional distributions. And there are certain conditions under which this works, but they are formal conditions. And spatial models, we have the same constraints. If the spatial conditional models play by the rules, then multiplying the conditionals together give you a proper joint distribution. If they don't play by the rules, you don't get a proper joint distribution. So that is the main distinction between the two. When you go from the other end, it always works, because the joint distribution is, if you wish, much more complicated than dealing with the conditionals. So there's much more involved in getting that specified. I just wanted to get this maybe not clear in your mind, but at least make you aware of it. If it's not familiar, you might want to refer back to a multivariate analysis text, or most econometrics texts have this in there somewhere. It's very easy to do in a normal distribution. Once you move away from the normal, it's a pain, because then these various things no longer hold, and you have to basically derive what the moments are for each specific case and how they combine together.